Hello, this is Unlock Circuits 18EC42, Module 3, Lecture 1, Part 1, Feedback Amplifiers. I'm Dr. Nirmala Sharif C, Professor and HOD ECE, CCAP Institute of Engineering and Technology, Vijayawada. So we'll be discussing here about the general feedback structure, some properties of the negative feedback, then the four basic feedback topologies, the series shunt feedback, series feedback, shunt, and shunt series feedback amplifier. So first we see that there are no electronic circuits where feedback is not present. So feedback is present in all types of electronic circuits. There are quite a good amount of advantages of negative feedback, and those are desensitizing the gain, reducing the nonlinear distortion, reducing the effect of noise, controlling the input and output impedance, extending the bandwidth of the amplifier. So what we do in the negative feedback is to trade off the gain, allow for the reduction of the gain by obtaining the other desirable properties. So we also see that already we have seen in the oscillators that positive feedback is the one which is used in oscillators. The general structure of the feedback amplifier is shown over here, where we are putting an amplifier and a feedback network with a load and the source. So we try to sample or take out some of the output and then multiply with the, take out the output over here and multiply it with the feedback factor beta, and whatever we get, that is the sampled output, and then we mix this with the signal source to get the input. So the sampling is done here from the output side, and mixing is done at the input side. So from here we can clearly make out that X0 is equal to A into Xi. X0 is equal to A into Xi, and except the feedback voltage here, feedback current over here, feedback signal over here is equal to beta into X0. Then Xi value itself is the XS minus XL. Xi is XS minus XL. We are mixing here as plus and minus, therefore it is XS minus XL. In the oscillators, both will be positive, whereas in the power, later we remove the source itself in oscillator, but here we have positive here and negative here. So therefore now what we can do is, in the equation here you can substitute this, that is, in place of Xi you can substitute XS minus XF, and then in place of XF we can substitute beta X0. Then you can expand it and take the term corresponding to the X0 on the left hand side to the right hand side, take the common X0 and then write X0 by XS, then we'll get A divided by 1 plus A beta, where beta is the feedback factor, AB is known as the open loop gain, and 1 plus A beta is the amount of feedback, and sometimes people call it the closed loop gain. And then the A beta, if it is greater than 1, if A beta is greater than 1, that means far greater than 1, you can neglect this, then AA will cancel, and we are left with 1 by beta. So that means AF is approximately equal to 1 by beta. The gain of the feedback amplifier is almost entirely determined by the feedback network. The gain of the feedback amplifier is almost entirely determined by the feedback network. That is what it means by this. AF, the gain of the feedback amplifier, is totally determined by the beta network. It's almost equal to 1 by beta. The feedback signal, that means if you substitute back xf is equal to bit in the equation xf equal to beta x naught, the value for x naught from over here, right? We will get a beta a or a beta divided by 1 plus a beta into the value of xs. And that is what we have here. Now let us consider some properties of the negative feedback. Those are gain desensitivity, bandwidth extension, noise reduction, and reduction in the nonlinear distortion. So let us see in detail each one of these. So AF, we have already written x naught by xs is equal to a by 1 plus a beta. And let us assume that beta is constant over here, and then we try to differentiate this AF with respect to A. So you can consider this as this expression as u by v, u by v. Then the differentiation of that will be vu dash minus uv dash divided by v square. This is u and this is v. Then you can write vu dash minus uv dash divided by v square. So if you do that and simplify, then you are going to get 1 by 1 plus a beta whole square. And this dA, if you take on this side, then you get this. Then we can divide this dAf by AF, the dAf by AF on both the sides, and then substitute on the right hand side the value of AF from here, A by 1 plus a beta. Then we are going to get this 1 by 1 plus a beta into dA by A. So what does that mean? It just means that the percentage change in AF is equal to the percentage change in A divided by 1 plus a beta. That means percentage change in AF, the feedback amplification, is reduced by the amount 1 plus a beta for whatever percentage change in A is there. So if A changes due to some reason, then TAF changes only by the change in A divided by the value of 1 plus a beta. So that is what we have here. Hence, we call this 1 plus a beta as the desensitivity factor. Then we also see that the feedback tries to provide us the bandwidth extension. So consider an amplifier whose high frequency response is characterized by a single pole. So we will consider over here that consider amplifier whose high frequency response is associated with this. So here, this is the upper 3 dB cutoff frequency. Now, if this upper 3 dB cutoff frequency is infinite, then we will have this as 0, and we are left with AS equal to AM. So midband gain will be equal to the AS will be equal to midband gain only throughout if upper 3 dB cutoff frequency is infinite. So this is the upper 3 dB cutoff frequency. Now, if we try to apply negative feedback, then we are going to get AFS is equal to AS divided by 1 plus beta AS. And in place of this AS over here, these two AS over here, we can substitute the AS value, rearranging the whole thing over there, then we are going to get this. So from this you can see that the new value of the mid-band amplification is the one which is associated with this, which is again 1 plus AM beta less divided by 1 plus AM beta with respect to this. This is divided by 1 plus AM beta. Then we'll get the mid-band gain value after the feedback. And also we see that in place of the omega h, we have here omega h into 1 plus AM beta. So that means the 3 dB cutoff frequency is increased by the value 1 plus AM beta. So that just gives us that the upper 3 dB cutoff frequency is increased by 1 plus AM beta, and the lower 3 dB cutoff frequency we see similarly that it is reduced by the same amount 1 plus AM beta over here. So thus we see that the bandwidth overall, generally the you know uh, bandwidth is almost equal to the upper 3 dB cutoff frequency if we neglect the lower 3 dB cutoff frequency. So hence we say that the bandwidth also increased by 1 plus AM beta. So that's we have bandwidth extension. Another property of the negative feedback is the noise reduction. Now, in general, the noise gets added to the, at the input side over here before amplification, and it might get amplified by the same amount as the signal source. So we try to write here the input signal Vs, the noise signal Vn, and the output signal is V0, and the gain of the amplifier A1. Then the signal to noise ratio is generally written as S by N. Signal is our Vs signal at the input, and at the output the signal is the noise is Vn, so Vs by Vn. So this is the signal to noise ratio at the input side. Equally well, the output signal V0 will become A1 into Vs, and output noise will become A1 into Vn. So therefore, the output signal to noise ratio also will become Vs by Vn. So if we have negative feedback, we have here the what you call amplifier, which is under test, and this is a clean amplifier. Whatever we have here, we have put over here, and this is a clean amplifier connected over here. Then the value of the V0 will be, you need to take out this value, so that will be Vs multiplied by A2 A1 or A1 A2 divided by the feedback arrangement, which corresponds to 1 plus A1 A2 by A1 A2 into beta. And the noise will be, the noise component will be the value of Vn is multiplied by A1, and then you have the feedback arrangement over here, which will correspond to 1 plus A1 into beta. So now, if you, what you call, take the signal to noise ratio of this, then that will just give us Vs by Vn into A2. This is the signal, right? This is the noise. Now, this is the signal and this is the noise. So if you divide S by N, then you have this divided by this, and that will be Vs by Vn into A2. So it just means that the signal to noise ratio is increased by the value of the clean amplifier, whatever is the clean amplifier we are connecting over here. So we would like to have the signal to noise ratio as large as possible. Signal should be very large, noise should be very less. So that means signal to noise ratio should be very large. To have a large signal to noise ratio, A2, the amplification of the clean amplifier, also should be quite large. Another of the very important property of the is the reduction in the nonlinear distortion. So here we are considering the what you call the transfer characteristic of the amplifier before feedback as this. Before feedback, the transfer characteristic. Transfer characteristic just means output versus input. Output versus the input. So and that value turns out to be, what is that? So here you can see that we are assuming that the amplification here is 1000. Then we have the amplification here, which is 100. Then the amplification here, which is 0. So open loop voltage transfer characteristic of the amplifier changes from 1000 to 100 to 0. So then we apply the negative feedback. Now, this negative feedback will assume that it is having a factor which is beta equal to 0.01. Then we'll get the value of AF1 as 1000 by 1 plus 1000 into 0.01, that is equal to 90.9. And AF2 is equal to 100 divided by 1 plus 100 into 0.01 is equal to 50. So for the segment which is here, we'll have AF1 is equal to 90.9 after feedback. And for the segment over here, we'll have the AF2 equal to 50. So this slope becomes this slope becomes this. So the slope of this is 90.9. The slope of this is 50. So 1000 reduces to 90.9 and the 100 reduces to 50 over here. So thus we have a change in the slope considerably, so reduced from the original one. So thus we have the reduction in nonlinear distortion. So we'll stop at this for today. For this lecture, we'll take up the next lecture.